We're starting a new section today, which is section 6 for no obvious reason, which is to do with stars. All right. You might be wondering when this was coming. Astronomy is obviously to do with stars, hence the name. And today what we're going to have a look at is how stars are made, how they exist, and how they finally die. In other words, the evolution of stars. Okay, you know that animals evolve, and you probably know that the landscape of the Earth, mountains and seas and things, they evolve. But amazingly, even stars do as well. But the evolution of stars, and a good way to think about this is do it like a little flow chart. The first stage in the evolution of stars is called a nebula. Some books call it a protostar. I don't know why, but you'll hear both words used together. All right. A nebula is very simple. It's just a big cloud. There's a picture of one on the board there. It's a famous one called the Orion Nebula. And it's basically made of, now let's get this right, it's made of hydrogen nuclei. Okay, not atoms. These little dots are nuclei from the hydrogen atom. If you zoomed in on one of these, what would it look like? It would look like a proton, because that's what it is. Okay? If you got some hydrogen gas, can you imagine doing that, getting some hydrogen gas? If you zoomed in on that, what would you see? You would see a proton with... Do you follow? That's hydrogen gas. That's a hydrogen nucleus. So 2 words never to use in this section, gas and atom. There are no atoms and there are no gases. What you're looking at on the board there, I'm sorry it's hard to see. It's much better on mine. What you're looking at on the board there is a nebula, which is made of a huge cloud of hydrogen nuclei. Okay? Not hydrogen atoms, as it says in many books. You might ask, why is that? And it's because the universe is mostly made, here's a quick drawing of the universe. The universe is mostly made of hydrogen. Okay? We'll come back to why that's true a bit later on. But we'll take that as our starting point for the moment. The universe, from the Big Bang, is mostly full of hydrogen. That's why chemistry is a bit of a cheat, because with the periodic table of 92 elements or whatever, most of them are most of them are extremely rare. All right, hydrogen and helium pretty much account for the whole universe, and everything else, the other 90 elements, constitute a very, very tiny fraction of the universe. So the universe is made of hydrogen. Okay, hydrogen nuclei. And this is the bit people find hard to understand. What's going to happen if you get some hydrogen nuclei like that is the force of gravity is going to pull them towards each other. Now you might say, well, hang on a minute, that's just bonkers. What's the smallest thing whose gravity concerns your life? Does the Earth's gravity affect you? It does, doesn't it? Does the Moon's gravity affect you?
Yes, but very slightly.
What things happen around you because of the Moon? Tides, which you get a lot of, Skipton, don't you, actually? But if you live near the sea or you go to the seaside, tides and stuff, and all that sort of thing. So the Moon affects you. I think the smallest thing I've ever found is the Himalayan mountain range. Himalayan mountain range, and this was a guy called George Everest, went surveying in Victorian times. He went to survey the Himalayas, and he found, you know those things that surveyors used to use, like a plumb line, like a piece of metal on a string to get a vertical and all that sort of thing. He found he was getting dodgy results, and it was because of, can you imagine the sideways gravitational pull of the Himalayan mountain range? If you've got the Himalayan mountain range on that side, that's probably got just enough gravity that if you hung a piece of string with a weight on the end, it wouldn't actually, can you imagine that? It wouldn't actually sit perfectly vertically. And he was doing very accurate work. He was surveying India, making maps of that part of the world for the British government, and he found that all his results were ever so slightly off. And he worked out it was because of the gravitational pull of the mountain range. So I think the smallest thing whose gravity ever bothered anybody is a mountain range. What are we talking about here? Individual nuclei from the centre of an atom. So tell me about the size of this gravitational force. Absolutely. It passed tiny a long time ago. It's way off down the street towards absolutely infinitesimal. You probably can't get how small it is on your calculator, even if you've got standard form. It's just going to be ridiculously small. So this part of the life of a star takes simply ages. All right? Because how quickly is the force of gravity going to pull these hydrogen nuclei together? Very, 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 very slowly. But the universe is a patient thing. It's got a lot of time, and also it's a bit like push starting an articulated lorry. Here's two hydrogen nuclei. Yes, you might say the force of gravity between them is teeny tiny. Okay, so it very gently moves them closer together. What will that do to the size of the gravity force? Makes it bigger, which moves them. Can you see? It is an accelerating process. Do you see? It is very slow. It is a very small force, but it will accelerate. As I said, it's a bit like trying to push start a lorry. Very, very slow to get it going, but as you get it going, you get more momentum and so on. All right? So this is stage one in the life of a star, where it is a nebula. Okay? At the moment, that's the top and bottom of it. There's nothing else going on. Gravity is pulling them together. Okay? They're not shining. They're not producing any light. They're not producing any heat, which makes this photograph rather strange if you think about it. If, as I've told you, this picture of the Orion Nebula is a bunch of hydrogen nuclei all being pulled together by gravity, why is it quite surprising that we can actually photograph it? Where's the light coming from?
The star's behind it.
Yeah, there's got to be something in there, hasn't there, to light it up. All right? Don't confuse it with your chemistry. It's got nothing to do with hydrogen gas and stuff like that. There's just hydrogen nuclei in a vacuum. All right? There's no light being given out. There's no energy production there. So where is what's going on? Now, this is a bit tricky. What you need is other stars. And that's the reason you can see the Orion Nebula. Yes, you've got this lovely great splodge of hydrogen gas with its famous red colour. You might think, I've never seen hydrogen gas going red. Well, that's because we're talking about hydrogen nuclei. If you get them all excited, they glow and they give out a red colour. So, what happens here? You could say, for a D-grade answer, you could say the star lights up the cloud of hydrogen gas. I'm not quite sure where to start with that sentence because it's just so wrong. The star lights up. Well, it doesn't use its light. There isn't any hydrogen gas. Okay. What happens is radiation from the nearby stars, usually things like ultraviolet or X-rays. Okay. What that does is it hits the hydrogen nuclei. Okay. And you can't see any of this. You can't see ultraviolet. You can't see X-rays. So ultraviolet, X-rays, things like that, produced by nearby stars, they basically excite, that's the word you need to use if you want to explain this in the exam. They don't light up the nuclei, that's just bonkers, you can't see an individual nucleus. What they do is they excite them, they transfer lots of energy, okay? And what happens is the little nuclei get very excited and they jig about and they re-emit that energy as visible light, which your eyes can see. Okay? So where is this lovely red light which we're seeing here, which has been photographed here on this picture of the Orion Nebula, is stars inside the nebula, stars behind the nebula are giving out things like ultraviolet. That ultraviolet hits the nuclei in the nebula and they re-emit it as light which you can then see, and in this case it's red light. Okay? This process is happening in this room, in these tubes. Okay? These tubes are called... That's it. This process is called fluorescence. Okay? And what you basically do is you cause the atoms in the nuclei, beg your pardon, in the nebula to fluoresce. Okay? They basically re-emit it at a different wavelength. All right? Very short wave radiation from the nearby stars. Not their light. It's not the light from the nearby stars. Don't think of the Orion Nebula like a big cloudy thing that you can't see very well. And nearby stars are like a torch. Do you follow? And that means you can see the paper because the stars are lighting up the nebula. That's 90% wrong. All right? There's nothing to see in the nebula because it's just hydrogen nuclei. There's nothing to see there. But what the nearby stars do is they excite the nuclei and make them emit visible light. Okay? It's a process called fluorescence. And for that reason, the proper name for this nebula, because there's several nebulas in this story, this is called an emission nebula. Okay? Stars light up the atoms in the nebula might get you 1 mark, because it's the right sort of idea, but it isn't lighting it up like shining a torch on a piece of paper. It's a bit more complicated than that. Okay? But that's why you can see the Orion Nebula. The stars behind it are putting ultraviolet and X-ray energy into the nebula, and it re-radiates it as red light. Okay, so that's stage one, the life of a nebula, and it takes an awfully long time. Okay, stage one takes simply ages. All right, until there's a better picture. That's a more modern picture of the Orion Nebula. Okay, so it's the stars around it whose ultraviolet light is making the nebula glow, making it visible. Okay. Stage two in the life of a star is when it becomes a stable star. It has a rather grand name. It's called a main sequence star, which simply means a stable star. Okay? Now, what's happening here is rather different to what's happening in a nebula. Okay? What's the nebula going to do over a long period of time in terms of its size if this process carries on? You've got gravity pulling everything towards everything else.
Retract.
Yeah, it's going to get smaller, isn't it? So if you started off like this, then gradually over a period of time, it's going to get smaller. What's the only force acting in this nebula is gravity. There's no other forces because the particles are too far apart, and so gravity is going to make it smaller and smaller. Okay? Now, what's that going to do to the temperature, the pressure, and the density in the middle? If you get a big bunch of gas, you might have done this with your bicycle pump, something similar, and you make it smaller and smaller, it's all going to go up, isn't it? So the temperature and the pressure and the density at the centre is going to go up. Okay? And very importantly, it'll reach a point where that temperature reaches about 10 million degrees. Okay? 10 million degrees is a very, very important temperature. Okay? Because at 10 million degrees, you can start to do this process. You can get hydrogen nuclei, not little solar system-like atoms, but actual individual nuclei. You can get them so close to each other that they stick together. And instead of being a nucleus of one proton, they become a nucleus of two protons. Now, if you know your periodic table, you've seen your periodic table in chemistry labs? Hydrogen is 1, helium is number 2. So what you've actually done there is that nucleus is no longer the centre of a hydrogen atom, it's now the centre of a helium atom. The process you've done here is a very grand name. It's called nuclear fusion. Not to be confused with nuclear fission, F-I-S-S-I-O-N, which is where you take very large nuclei like uranium and you persuade them to split. Do you follow? That's the thing that's used in nuclear bombs and power stations and so on. Nuclear fusion has yet to be made into a power station, but hopefully in your lifetime might happen. And the other thing you produce when you do this is enormous amounts of energy. The energy released when you do this is absolutely huge. This is where Lord Kelvin had his mistake. If you think a bucket load of magnesium can give you a lot of energy, or a bucket load of gunpowder, a bucket load of nuclear fusion will give you 7 powers of 10 more, 10 million times more energy. Okay? And this is how stars have enough energy to last for thousands and thousands and millions of years. Okay? If stars did chemistry, Lord Kelvin was right, they'd all be over by about 8,000 years. But stars do nuclear fusion, where the energy from each reaction is 7 powers of 10 greater. Okay? A good way to think about this is that hydrogen nuclei have little hooks on them, like Velcro. I've never seen a textbook that encourages you to think about this, but it's actually a good way of thinking about it. Most forces you're aware of, like gravity and magnetism, go on forever, don't they? If I get two magnets, if I put them further apart, the force of magnetism goes down. Where could I put them so the force of magnetism was 0? You can't, can you? If you put them either end of the universe, is the force actually 0 or just very small?
Very small.
It's just very small, isn't it? The forces in the nucleus are different to that. There's a very famous force called the strong nuclear force, and it's a really important one because it holds everything together. If you've done nuclei and atoms in your chemistry lessons, the question that you ought to be asking is 92 protons, which one's that? Anyone know? It's a famous one, number 92 on the periodic table. Last natural one is uranium. Contains 92 protons. Protons are all positively charged. Get 92 positively charged things and squash them into a teeny tiny space like that. What would you expect them to do? Yeah. Why doesn't every single nucleus, apart from hydrogen, explode? But think about it, even helium's got 2 protons. So next time in a chemistry lesson, chemistry teacher says this, the nucleus of hydrogen contains 2 protons. That's just mental, because they just repel each other, wouldn't they? And they're really, really close together. The nucleus is about the smallest thing you can imagine. And uranium, what on earth's going on there? Okay? The answer is something called the strong nuclear force. Okay? The strong nuclear force, if I get 2 pens and say how much strong nuclear force between these 2 pens, nothing. Not it's really small, absolutely nothing. It doesn't exist. What if I put them so they are about a micron apart? With me, the surface of that looks smooth to you, which means the bumps are smaller than 1 micron, 10 to the minus 6 millionth of a metre. So they're not touching, they're about 2 millionths of a metre apart. How much strong nuclear force? Nothing. The strong nuclear force is like Velcro. Hold 2 pieces of Velcro very close but not touching. How much strong nuclear force? Nothing. Once they touch each other, you see, they lock together. Strong nuclear force holds together every single nucleus after hydrogen. Okay? How do you get these nuclei to get very close together? Because the problem is, why don't they want to go close together? Why won't they naturally stick together like this? 2 hydrogen nuclei? Yeah, they're both positive. The only way to do it, here comes the temperature thing, the only way to do it is to get them moving very fast. It's a bit like a car crash where the 2 drivers can't swerve. If they approach each other if you get the hydrogen nuclei very hot, then they'll come together, but the positive repulsion will just push them away. If you get them going really fast, they come zooming up to each other and lock together before the positive nest can repel them. Okay? So basically this process is called nuclear fusion. It requires a temperature of about 10 million degrees, so the hydrogen nuclei haven't got time to repel each other. Okay? And it produces immense amounts of energy. Okay? What we're starting to form now is, as I said, is a star a bit like the Sun. In the core, you've got large amounts of energy being produced by this process called nuclear fusion. And this is why stars shine. Yeah? Because at their cores, they're producing huge amounts of nuclear energy. The question then is, why do stars stay like this? The Sun has been around for thousands of millions of years. It will be around for thousands of millions of years more. It does seem awfully stable. And yet gravity is going to be very, very strong indeed. Gravity is pulling the Sun in very, very strongly. It always does, has done right from the beginning of the nebula. A nice way to think about this is that a main sequence star has reached an equilibrium. It's reached a balance point. Think of it like a little seesaw. The little seesaw for the nebula isn't like that. A nebula is runaway gravity. Nebulas are all getting smaller because gravity is making them smaller. But when you get to the main sequence star, nuclear fusion enables it to reach a sort of a stable point where it can stay for a few thousands of millions of years. All right? On one side of the balance is the very strong force of gravity, and on the other side of the balance is what's called radiation pressure. Okay? As the energy from the star comes outwards, it actually has to push its way out. So think of a star like the Sun, a main sequence star or a stable star. Gravity's pulling in, but balancing the gravity is the light and the X-rays and the gamma rays and all the energy produced by the nuclear fusion at the core is having to push its way out of the star. Now, the idea of light having to push its way through something doesn't make sense. You don't go into your bedroom at night, flick the light switch and go, oh, blimey, that light's a bit strong, isn't it? It's nearly knocked me over. The idea of light pushing on you doesn't seem to make much sense. It's a true piece of physics. It's called radiation pressure. What's the radiation pressure from these lights? Way too small to ever even write down. Okay? But it's a true fact because the centre of the star, particularly, is very dense. And literally the light has to fight its way from atom to atom, and it ends up exerting a force outwards. It's a bit of one of those bits of physics I really can't show you. If you imagine the sun had like a bathroom light pull, imagine here's the Earth orbiting the sun. If I turn the sun's light off, the Earth would orbit slightly closer because the sunlight isn't pushing it out anymore. It's a force of about 4 tons. The sun's light pushes on the Earth with a force of about 4 tons. You with me? Now 4 tons, obviously on a thing the size of the Earth, isn't very much, but it's a true force. It really does exist. Okay? Light has to push. When light hits something, it pushes on it. In most situations, you're never going to come across that amounting to anything. But in the centre of a star, where the density of the material is very, very high, radiation pressure gets very big. And in fact, this is the thing I want to leave you with, I think, is that. That's what we mean by a stable or a main sequence star. It's where nuclear fusion has switched on at the centre of the star. It's producing all this electromagnetic radiation, light and gamma rays, X-rays, etc., and they're pushing outwards so strongly that they balance gravity. Okay? And that's how you form a stable or a main sequence star like the Sun. Okay? Have you ever been told by your physics teacher that the Sun is 8 minutes away? If the Sun went out now, we wouldn't know about it for 8 minutes, because why? The light would take 8 minutes. It's 93 million miles, isn't it? The light takes 8 minutes to get here from the Sun. That's not quite true. It is 8 minutes from the surface of the Sun to the Earth. That's 8 minutes. It's about 100,000 years. Think about it. A piece. If you look at the Sun, look at the Sun. If you were to look at the Sun and think, gosh, here comes the sunlight. 8 minutes ago, that left the Sun. True. It left the core of the Sun 100,000 years ago. You with me? Next time we see the Sun, if we ever do, next time you see the Sun, look at that. Don't stare at it, obviously, but the sunlight around you left the Sun 8 minutes ago, as your physics teacher tells you. But actually, it left the core of the Sun 100,000 years and 8 minutes ago. Do you get the idea that this light has to force its way out? I know it sounds like a mad sentence, but in the centre of the Sun, the centre of a star, that's absolutely true. The light has to force its way out, and it produces a force, this is the thing to hang on to, equal in size to the force of gravity. Okay, and that's how stars remain stable. Final phrase to finish on. Why do stars shine? Because they have to. If they didn't, what would gravity do? Start to crush them, and that's a good way to think about what we're going to do next time. All right?